Today we're going to talk about something called standing waves. And so far we've only seen one kind of wave, which is the usual kind of wave, which are propagating waves. So it's a wave that moves in a certain direction, so either this way or this way. However, for example, if you have a guitar, the waves really have nowhere to go, right? So you have a string like this, and what you see is that, yes, there is a wave moving here, but all that happens is that the string goes up and down, up and down, up and down. And these 2 points that are attached to the different ends of the guitar, they never move at all. So we call this a standing wave because there's points that don't move at all, and because it's a wave that is strapped, and it basically just oscillates up and down. It doesn't propagate. Now what we're going to do today is to learn to calculate the frequency of a standing wave based on the length of the tube or the string that contains it. Now this, as always, is pretty commonsensical, and you could do this yourself each time. So there's really no need to memorize any of these formulas, but there is a need to understand what we're doing. So imagine that we have a string of length L, and there's a wave in here, and we hold these 2 points fixed, so they're not allowed to move. This means that there's a wave that goes up and down like this. And then we ask ourselves, well, what are the possible wavelengths that are allowed in this? And of course, the first one that one can think of, well, first let's name this, let's call this length L. The first one that one can think of is, of course, this one, right? Now, this thing has the condition that these 2 points are fixed, and it's going to bubble up and down like that. So what's the wavelength of this thing? Well, this would continue exactly this much, right? So this is exactly half a wavelength. So the wavelength of this thing is then 2L, because it's twice the length of the string. But this is not the only wave that we could have here. So for example, we could have this wave in here. So something that does this, right? Now in this case, the wavelength is exactly the length. So we would have that lambda equals L. But we're not done yet, because we could have this other wavelength. Well, I'm running out of colors. Let's see if I can, let's make this green. All right, and then in this case, we would have something like this. And now what we need to do is just try to figure out, so this is one wavelength, so this is one wavelength and a half. So we have that lambda will be 2L over 3, because lambda is 2/3 of L, right? So 1, 2, 3/3, and the wavelength is 2/3. And now hopefully you start to see a pattern, because I can rewrite these things like this. So for example, this one I can rewrite as lambda equals 2L over 1. Then I can rewrite this one as lambda equals 2L over 2. And then I can rewrite this one as lambda equals 2. Well, actually, I don't rewrite this one because it's already the same. But if you take a look at this, it always has the same pattern, right? It's 12 over a number, and then this number gets bigger and bigger and bigger. So we can deduce then that the wavelength of any wave, any standing wave, when the 2 points are fixed, has to be lambda equal 2L over n, where n is an integer. Good. Now, however, we have other types of waves, of standing waves, that have a different formula for the wavelength. Let's check them out. Now, another possibility is that one of our points is fixed, like this, but the other one isn't. Now, if this happens, of course, the wave here is free to move as much as possible, which means that this here should be an antinode. Now, remember that in a wave, we have, well, something like this. Now, if this is a standing wave, this point here does not move, this point here does not move, this point here does not move. These are called nodes. Then these things here will move, and this part here will move the most, right? So it will go up, down, this one will go up, down, and so on. These things here are called antinodes, and these things here are called nodes. So here we'll have a node, and here we will have an antinode. So we will have something like this. So the first possibility is a wave that does this. Now, again, we would like to know what the wavelength is for this. Well, if this is L, again, then what we do is we make these a little longer. So like this. We've got and then like that, right? So you can easily see that from here to here, which is half a wavelength, that's 2L. So therefore the whole wavelength is 4L. So for the first case, we've got that lambda equals 4L. Alright, and again, we have more options than this, right? So the next option is this. We can have, so this ends as an antinode always, and then we can have that, right? Now if we take a look at this, what we can do is, again, expand our wavelength a little bit more here, and we can see that this is 3/3 of L, and that if we add one more third, we get a full wavelength, right? Therefore, the wavelength is 4/3 of L, and hopefully you will start to see a pattern. Now the next one would be something like this. So again, it ends here as an antinode, and then whoop, whoop, whoop. Okay, and here we do exactly the same thing that we did before. We got 1/4, 2/4, 3, 4/4. So that's lambda. And we see that each one of these quarters is a fifth of L, right? 1, 2, 3, 4, 5. So basically, lambda is 4/5 of L. So let's write that down. Lambda equals 4/5 of L. And hopefully you've seen a pattern already, right? We got that lambda has to be equal to 4/n of L. Now you can write it like this, where n equals 1, 3, 5, etc. And that's the way the book does it. I personally prefer to be a little bit more precise and not allow any confusion. Now, if you write the formula like this, then you can allow n to be any integer, and this works all the time. So that's the way I would write it. This ensures that this is an even number, and you don't even have to think about the fact that this is an even number. Anyway, so here's the formula that we get for the wavelength when one of the ends is free. Now, what happens when both ends are free? Well, when both ends are free, things are actually very easy, because take a look at this. So we have something like this, and what we have is that our wave does something like that, and both of these are antinodes. And now you can easily see that this is exactly the same as having node, node, and this, right? This is half a wavelength, this is half a wavelength. It's just been moved a little bit, but it's the same thing. Therefore, whatever formula is valid for the wavelength of a wave that's attached in both points is also going to be valid for a wave that has both ends free. So, piece of cake. Now, one last thing that I would like to talk about is resonance. And we already talked about this when we were doing oscillations, but we didn't actually calculate anything with it. But now that we know about stationary waves, we can actually do calculations with resonance. And remember that the resonant frequency is just a so imagine that I have, I don't know, a metal bar. The resonant frequency is the frequency at which this metal bar starts absorbing all the energy that I send it. And for example, if I get something to oscillate at the resonant frequency, it will absorb energy very fast, and it will be possible to break it, for example in a bridge, etc. However, we're not talking really about oscillations here. We're talking about waves. So let's imagine I have a building. Here's my building, and let's just say that it has a certain height L. And there's an earthquake. Now, if there's an earthquake, the ground is shaking. So this thing is an antinode. and there's nothing holding this together. It's not, it's not stuck to the sky. So therefore, these will also be oscillating, and these will also be an antinode. So what we have is really a stationary wave where this is the node and these are the antinodes. And therefore, the formula that we found for the two fixed points applies, as we just saw before. So we ask ourselves, what's going to be the first resonant frequency of this thing? Well, remember, the first resonant wavelength was 2L, right? Now, if we want to find the frequency, all we need to do is to use the wave equation, which, remember, is just this velocity time thing, right? So we have that distance equals speed times time, or speed divided by frequency, right? So then, using these two things together, we can find out the resonant frequency of the building, where this C does not stand for the speed of sound in air, but it stands for the speed of sound in the building, so through the solid in the building, because remember, the waves are propagating through the building. So then we can see that the frequency, so C over F has to be equal to 2L, and then of course then F equals C over 2L. And this is the resonant frequency of our building. So, well, hopefully you will not use this new power for evil, but if you are unlucky enough that you are in an earthquake and the vibration of the ground is exactly the frequency of your building, then you are in a very bad spot. So that's that. Now, if you know how to do these two things, first deduce the allowed wavelength of standing waves and explain what resonance is, and deduce an expression for the frequency, then you've learned what you had to learn in this video. And now all that's left is for you to do problems, and hopefully it won't be too much of a hassle. I'll see you tomorrow.